How do you build a city where cities cannot exist? What kind of madness drives people to look at a shallow lagoon of mud and water and declare, "Here, on this impossible marsh, we will create marble palaces and stone churches"? Can wooden stakes hammered into underwater clay truly support an entire civilization for more than 1,000 years? Venice shouldn't exist. Engineers examining the Venetian lagoon would declare it the worst possible location for construction. Soft mud that offers no stable foundation, tidal waters that rise and fall twice daily, salt that corrodes everything it touches, and ground so saturated that every step sinks slightly as water displaces beneath your weight. Yet Venice rose anyway. Not a small fishing village clinging to the few stable patches, but a sprawling city of 118 islands connected by 400 bridges, a maritime empire that ruled Mediterranean trade, a place where every building stands on millions of wooden poles driven deep into clay that should never have been asked to support such weight. Imagine the 5th century refugees fleeing barbarian invasions, arriving at the lagoon's edge with nothing but desperation and determination, looking out at marshland where solid ground refuses to form and deciding this would be their home. Imagine hammering tree trunks into underwater mud for years, decades, centuries, never seeing the palaces and churches that would eventually rise, working only on faith that wooden pilings could create foundations where nature provided none. 10 million wooden stakes, maybe more. Oak and larch forest cut down and transported across the Adriatic, then driven into the lagoon bed one exhausting blow at a time, disappearing beneath brown water with no immediate evidence they were accomplishing anything at all. Those wooden pilings are still there tonight, buried beneath Venice for 800, 1,500 years, still holding steady despite carrying loads of marble and stone their installers never imagined. The wood hasn't rotted because it's been underwater without oxygen all this time, preserved by the very element that should have made construction impossible. Venice floats on ancient forests that no one will ever see again, wooden ghosts supporting stone reality, proof that human determination can convince even a lagoon to become solid ground if you're willing to work long enough, dig deep enough, and refuse to accept that some places are simply too impossible for cities. Welcome to the sleepy structures, where the world's greatest construction achievements become gentle companions for your journey into sleep. This channel explores buildings, bridges, and cities through calm storytelling that honors the years of patience and labor these projects required, not through dramatic tension that keeps you awake, but through peaceful narration that allows your mind to rest while learning how impossible dreams became permanent reality. Now close your eyes whenever you're ready. The city on water will keep building whether you're awake or dreaming. The Roman Empire's collapse in the 5th century unleashed chaos across the Italian peninsula. Barbarian tribes swept down from the north, bringing violence that shattered the peace Roman legions had maintained for centuries. Cities burned, populations fled, and the certainties that had defined Mediterranean civilization for generations dissolved into uncertainty, where survival mattered more than prosperity or comfort. The people living along the northern Adriatic coast faced choices that previous generations had never confronted. Remain in their coastal towns and villages where Huns and Visigoths and Lombards arrived, with regularity to raid and pillage, or flee to places so marginal that invaders might not consider them worth attacking. The Venetian lagoon offered exactly that kind of marginality, a shallow expanse of water dotted with muddy islands and sandbars, a place where the Adriatic Sea met the Italian coast in a gradual transition zone that was neither fully land nor completely water, terrain so unstable and resource-poor that no one had bothered establishing permanent settlements there because solid ground existed just a few kilometers inland where construction made sense. Yet beginning around 450 CE, refugees began arriving in the lagoon, not as temporary shelter during raids, but as permanent relocation, families bringing what possessions they could carry and deciding that these marsh islands would become home regardless of how unsuitable they appeared for human habitation. The decision reflected calculation beneath its desperation. Yes, the lagoon offered miserable living conditions compared to mainland towns, but it also provided natural defense that walls and armies couldn't match. Barbarian cavalry that terrorized the countryside couldn't effectively attack across water, their horses useless in the shallow lagoon channels, their weapons and armor impediments rather than advantages when fighting required boats and knowledge of tidal patterns that locals possessed and invaders lacked. The earliest lagoon settlers established fishing communities on the few islands with reasonably solid ground. They built simple wooden structures. They learned to navigate the tidal fluctuations that twice daily transform the lagoon's geography, and they discovered that isolation, which made life difficult, also created safety that mainland populations envied as raids continued decade after decade. How does a refugee settlement of fishermen and salt workers transform into ambitions for permanent city construction? The transition occurred gradually across generations. As the lagoon community survived and even prospered through salt production and fishing, as trade connections developed with mainland towns that needed the lagoon's products, as populations grew beyond what the few naturally stable islands could support, the settlers faced the question of whether to expand or accept limits on growth that stable ground imposed. Expansion meant building on islands that were really just mud barely rising above water level. Ground so soft that structures sank, so saturated that foundations rotted, so unstable that storms regularly reshaped the entire lagoon geography and erased whatever improvements had been attempted. The conventional wisdom said you don't build cities on such terrain. You accept that some places exist for temporary use or marginal activities, but never for the kind of permanent construction that cities require. But by the 6th and 7th centuries, the lagoon communities had reasons to reject conventional wisdom. The Byzantine Empire, based in Constantinople, recognized the lagoon settlement's strategic value and granted them trading privileges that brought wealth beyond what fishing and salt could generate. The settlement, called Rivo Alto, later Rialto, emerged as a central trading point where merchants gathered and where governing councils met to coordinate activities across the scattered lagoon islands. The wealth from Byzantine trade created both the resources and the incentive for more substantial construction. Wooden buildings gave way to structures incorporating stone. Individual island settlements began seeing themselves as parts of a larger community, and the idea emerged that the lagoon could support not just survival, but genuine urban development if someone figured out how to build on ground that wasn't ground at all. The engineering challenge was obvious to anyone who had attempted construction on lagoon islands. You couldn't simply dig foundations the way mainland builders did, because there was no solid substrate to reach. just mud and clay and sand extending down meters before encountering anything resembling bedrock. Buildings placed directly on this soft material sank unevenly, one corner dropping faster than others, walls cracking as the structure twisted, the entire building eventually listing at angles that made it unusable or dangerous. Wood placed in the saturated ground rotted within years, destroying whatever foundations had been built, and the salt water that permeated everything corroded metals and degraded mortar that would have remained stable in mainland conditions. Yet the lagoon settlers needed to build upward rather than outward. The limited land area of stable islands couldn't accommodate growing populations, and every new resident required housing. Every merchant needed warehouses. Every church required substantial structures for worship. The solution emerged through observation of natural processes and experimentation with materials that behaved differently than builders expected. Wood submerged completely underwater didn't rot the way partially exposed wood did, because decay required oxygen that water-saturated environments lacked. Trees driven vertically into the lagoon bed with their tops remaining underwater would last indefinitely. They might not reach true bedrock, but they penetrated through the soft surface layers into denser clay below, and when many pilings were driven close together, they created what engineers would later call a friction pile foundation, where the combined surface area of multiple poles distributed weight across enough clay to prevent sinking. The lagoon builders didn't have engineering formulas or mathematical calculations. They learned through trial and error, through driving pilings for structures that succeeded or failed, through generations of accumulated knowledge about how many poles were needed for buildings of different sizes and which types of wood lasted longest in lagoon conditions. By the 9th century, the techniques for building on pilings had developed enough that substantial construction became possible. Not just wooden houses, but stone churches. Not just individual family dwellings, but warehouses and government buildings. Not just scattered structures, but concentrated development that began looking like an actual city, rather than a collection of fishing villages. The settlement pattern that emerged reflected the lagoon's constraints. Construction concentrated on islands where pilings could be driven most successfully. Canals between islands became transportation routes since building roads on such ground was impossible, and boats replaced carts as the primary means of moving goods and people, because water was the only reliable surface for travel. The decision to commit fully to urban development rather than remaining a collection of modest settlements came in 810 CE, when the lagoon community relocated its political centre from Malamocco to the Rialto Islands. A choice that acknowledged the lagoon wasn't temporary refuge but permanent home, that these marsh islands would be developed into something worthy of being called a city, that the engineering challenges of building on water would be solved rather than accepted as limits on ambition. The Doge, the elected leader of the Venetian community, moved his residence to Rialto. The bishop established his cathedral there, and merchants and craftsmen followed because political and religious authority created the markets and opportunities that drove medieval urban growth. What drives people to choose difficulty over ease, to build in lagoons rather than move a few kilometres inland to solid ground, where construction follows conventional patterns? Part of the answer was strategic. The defensive advantages that had protected refugees continued protecting the growing city, and Venice's location at the head of the Adriatic made it an ideal trading hub between Europe and the Byzantine East. But part was also identity. The lagoon settlers had survived when mainland populations suffered. They had developed techniques and knowledge that made them unique, and they had created a community that worked precisely because it was different from mainland cities. Building on, water wasn't just an engineering challenge to overcome. It was a defining characteristic that separated Venetians from everyone else, that made their city special, that turned impossibility into source of pride rather than limitation to escape. By the year 1000, Venice had committed irrevocably to the lagoon. The investments in piling foundations and stone construction were too substantial to abandon, the population too large to relocate, the identity too tied to being the city that rose from water where cities shouldn't exist. The question was no longer whether to build in the lagoon, but how to build bigger, better, grander. How to create churches that rivaled Constantinople's splendor, palaces that proclaimed Venice's growing wealth and power, bridges and canals that made the city function efficiently despite having water instead of streets. The answer to those questions would require millions more wooden pilings, stone quarried from distant coasts, innovations in construction technique, and centuries of labor by workers who would never see the completed city they were building, but who understood they were creating something permanent on foundations that would outlast everyone who ever questioned whether Venice's impossible location could truly support a great city's weight and ambitions. The commitment to permanent construction on lagoon ground required solving a problem that no previous civilization had confronted at this scale. How do you create stable foundations beneath buildings when the earth beneath your feet is saturated mud that compresses under weight, that shifts with tidal pressure, that offers no solid layer within reach of hand tools and medieval technology? The Venetian builders understood that simply placing stone or brick directly on the lagoon bed guaranteed failure. Structures would sink unevenly as the soft substrate compressed. Walls would crack as one corner dropped faster than others, and within years the buildings would lean at dangerous angles or collapse completely. The solution required thinking vertically rather than horizontally. If the surface layers couldn't support weight, then support must come from deeper layers, and reaching those layers meant driving wooden poles down through the soft mud into the denser clay below, where friction and compression could distribute loads across enough material to prevent sinking. The wood selection wasn't arbitrary, but reflected knowledge gained through generations of observing which materials survived lagoon conditions. Oak became the preferred species for pilings because its density and grain structure provided strength that resisted breaking under the hammering required to drive poles deep into clay, and because oak submerged in water developed a hardness over time, as minerals from the lagoon water gradually penetrated the wood fibre and essentially petrified it into something closer to stone than timber. Larch from alpine forests served as secondary choice when oak supplies ran short, slightly softer than oak but still durable, and more readily available from forests in the regions north of Venice, where rivers could float cut logs down to the Adriatic for transport to the lagoon. The trees were felled in winter when sap flow was minimal, trimmed of branches and cut to lengths typically ranging from 2 to 8 meters, depending on the depth of soft substrate at specific construction sites and the size of building being supported. How many workers does it take to drive a single wooden piling into underwater clay? The pile-driving teams developed specialized roles that medieval guild systems would later formalize into distinct occupations. The preliminary team worked in shallow water or on exposed mudflats during low tide, using long probes to test the substrate depth and identify where bedrock or dense clay could be reached, marking positions where pilings would be driven in patterns calculated to distribute the building's eventual weight. The driving teams operated pile drivers that were essentially tall wooden frameworks called pile engines that held the wooden pole vertically while a heavy weight was repeatedly dropped onto its top to hammer it downward. The weight, often called a ram or monkey, consisted of iron or stone masses ranging from 200 to 500 kilograms attached to ropes that ran through pulleys at the top of the pile engine framework. The driving process required coordination between multiple workers. Rope pullers who hauled the ram upward using their combined body weight, the foreman who judged when the ram had reached sufficient height and called the release, the guides who ensured the ram fell straight onto the piling top without glancing off to damage the pole or the framework, and the checkers who measured after each series of blows how much the piling had advanced into the clay. A single piling might require hundreds or thousands of blows depending on the substrate density. In areas where soft mud extended deep, the early strikes drove the pole downward rapidly with each impact, but as the pole penetrated into denser clay, the progress slowed dramatically until each blow might advance the piling only a centimetre or less. The workers learned to recognize when a piling had reached adequate depth not by measuring to some predetermined number, but by the sound and feel of the impacts. When the ram's blow produced a dull thud and barely moved the pole, they knew it had reached clay dense enough to provide support. What thoughts occupy a man's mind while hauling rope hour after hour to raise and drop a weight that drives a wooden stake into invisible mud beneath brown water? The pile drivers worked in conditions that combined exhausting repetition with a constant awareness that their labour's results remained hidden. Unlike stonemasons who could see walls rising, or carpenters who watched frameworks taking shape, the pile drivers spent entire days making wooden poles, disappear beneath the lagoon surface with nothing visible to show for their effort, except perhaps the top few centimetres of pole remaining above water. The work was wet and cold in winter when lagoon winds cut through clothing and when hands became numb on the ropes, and it was sweltering in summer when exertion under the Italian sun without shade drained strength and made men dizzy. The pay was modest because pile driving was considered unskilled labour, despite the physical demands and the expertise required to judge substrate conditions and coordinate the driving teams. A pile driver might earn enough for basic food and shelter, but rarely accumulated savings or achieved the status that skilled stonemasons or master carpenters enjoyed. The pile spacing followed patterns that combined mathematical calculation with practical experience. For typical residential buildings, pilings were driven roughly 1 metre apart in a grid pattern that covered the entire building footprint, creating a forest of vertical poles whose tops would eventually be leveled to the same height. Larger structures required denser piling arrays with spacing as tight as 50 centimetres, and the heaviest buildings like churches or palaces might have double or triple layers of pilings, driven to different depths to create a graduated foundation, where the deepest poles reached the most stable clay and the shallower poles filled the spaces between to maximize the distribution of weight. A modest 2-story house might rest on 200 to 300 pilings. A substantial palazzo could require several thousand, and the largest churches involved tens of thousands of wooden poles creating underground forests that would remain hidden forever once construction proceeded above water level. After the pilings were driven to adequate depth, their tops were cut off at a uniform level slightly below the expected low tide mark. This ensured that the wood would remain permanently submerged and protected from the rot that would occur if the poles were exposed to air and water alternately. The cutting required workers to operate underwater or during the brief low tide windows when the piling tops might be exposed, using saws that had been specially designed with teeth angled for cutting submerged wood where visibility was minimal and where the water resistance made conventional sawing motions ineffective. The levelled piling tops created a platform foundation, but wood alone couldn't support masonry walls. The Venetians developed a system where horizontal wooden planks called zatteroni were laid across the piling tops, creating a raft-like platform that distributed weight across all the pilings rather than concentrating loads on individual poles. These platforms were sometimes 2 or 3 layers thick, with the planks oriented in different directions to prevent any gaps where weight might concentrate. On top of the wooden platforms came layers of Istrian stone, a dense white limestone quarried from the Istrian peninsula across the Adriatic in what is now Croatia. The Istrian stone served multiple purposes in the foundation system. Its density and water resistance prevented the wooden platforms from degrading even if water occasionally reached them. Its flat surfaces provided stable bases for brick or stone walls, and its slight porosity allowed water that accumulated in the foundation to drain gradually rather than pooling, and creating pressure that might shift the pilings. The stone layers were typically 30 to 50 centimeters thick, composed of carefully fitted blocks that created a solid platform extending slightly beyond the building's eventual wall lines. Why does wood buried in oxygen-poor lagoon mud survive for centuries while exposed timber rots within decades? The preservation mechanism wasn't understood by medieval builders in scientific terms, but they observed the results and learned to trust what experience taught. Wood decay requires fungi and bacteria that need oxygen to metabolize the cellulose and lignin that give wood its structure, and when wood is completely submerged in waterlogged clay, the oxygen levels drop so low that these decay organisms cannot survive. The wood doesn't remain unchanged. Minerals from the water gradually replace the organic material through a process similar to fossilization, and over centuries the wooden pilings become increasingly stone-like in their hardness and durability. Modern analysis of pilings extracted during restoration work has found wood that was driven into the lagoon bed 800 or 1,000 years ago still sound enough to bear weight, its fibers intact, its structure solid despite carrying loads of marble and stone that original builders could never have anticipated. The scale of piling work required for Venice's development across centuries becomes staggering when calculated. Estimates suggest that more than 10 million wooden poles were driven into the lagoon bed over the course of medieval and Renaissance construction, representing entire forests consumed to create foundations that would remain forever invisible beneath the city. The economic and environmental impact of this timber consumption was profound. Forests throughout the northern Italian mainland and the Balkan regions were systematically harvested. Rivers were used to float millions of logs to the coast, and the Venetian government established forestry regulations to ensure sustainable timber supplies for the piling work that continued generation after generation as the city expanded and as old buildings were replaced with larger structures requiring new foundation work. By the 13th century, when Venice had grown into a major Mediterranean power, The wooden piling foundation system had proven itself through centuries of success. Buildings that had stood for 200 or 300 years showed no signs of the catastrophic sinking that skeptics had predicted. Churches built on thousands of pilings supported marble, facades and heavy tile roofs without distress, and the technique had become so refined that Venetian builders could calculate with reasonable accuracy how many pilings would be required for structures of any size. The hidden forests beneath Venice's palaces and churches represented not just engineering solutions, but accumulated knowledge passed from master builders to apprentices, written in guild records and construction contracts, refined through trial and error across generations who understood that their city's survival depended on wooden poles driven deep enough, spaced closely enough, and protected well enough to hold steady for centuries against the weight of stone and the pressure of water that surrounded them always, waiting patiently for any weakness that might allow the lagoon to reclaim what human determination had temporarily convinced it to surrender. The wooden pilings created foundations capable of supporting substantial buildings, but foundations alone don't build cities. Venice needed stone for walls and bridges, brick for residential construction, marble for church facades, timber for roof frameworks, metal for reinforcement, and countless other materials that the lagoon itself couldn't provide. The challenge facing Venetian builders went beyond ordinary construction logistics. They needed to transport massive quantities of materials to islands accessible only by boat, across water that changed depth with the tides, to construction sites where there were no roads for carts, no solid ground for storing materials, and no possibility of using the wheeled transportation that mainland construction relied upon. Every stone block, every timber beam, every barrel of lime for mortar had to arrive by water and be moved from boats to building sites through methods that combined medieval technology with innovations developed specifically for lagoon conditions that no other city faced. The Istrian stone that capped the wooden piling foundations came from quarries on the Istrian Peninsula, roughly 200 kilometers south across the Adriatic. White limestone that resisted salt water better than most alternatives, that could be cut into blocks of manageable size while maintaining strength, and that was available in quantities sufficient for a city that would consume millions of tons across centuries of construction. The quarrying operations in Istria employed workers who cut stone using iron wedges driven into natural fracture lines, who shaped rough blocks with hammers and chisels, who loaded the finished stones onto ox carts for transport down to the coast, where Venetian ships waited at docks built specifically for this trade. The stone blocks varied in size depending on their intended use. Foundation stones might weigh 200 to 300 kilograms each, large enough to provide stability but small enough that teams of men could maneuver them, while decorative elements and columns could be much larger, sometimes exceeding a ton and requiring specialized lifting equipment to load onto ships. The sea voyage from Istria to Venice depended entirely on weather and season. Favorable winds could make the crossing in 2 or 3 days, but storms forced ships to shelter in coastal harbors sometimes for weeks until conditions improved, and winter months saw reduced traffic because the risk of losing valuable cargo to rough seas outweighed the need for materials during the season when construction often paused anyway. The ships carrying stone were broad-beamed cargo vessels designed for capacity rather than speed. They sat low in the water when loaded. They required careful ballasting to prevent the heavy stone cargo from making them unstable, and they needed experienced pilots to navigate the shallow approaches to Venice, where shifting sandbars created hazards that could ground a heavily loaded vessel and require days of unloading and refloating before the cargo could reach its destination. How do you unload tons of stone from ships onto islands where no docks exist in the conventional sense? The Venetian solution involved waterfront areas called reeve, where the canal edge had been reinforced with wooden pilings and horizontal planking to create berthing spaces where boats could tie up directly against the island edge. Ships would maneuver alongside these reeve. Workers would extend wooden booms from the ship's mast to lift stones using rope and pulley systems, and the blocks would be swung over the water and lowered onto the river, where other workers received them and moved them to temporary storage areas or directly to nearby construction sites. The lifting was done by human power. Teams of men hauling on ropes that ran through multiple pulleys to reduce the force required, but even with mechanical advantage, a 300-kilogram stone demanded coordinated effort from 6 or 8 workers who had to maintain rhythm and control to prevent the load from swinging dangerously or dropping to shatter on impact. Brick production occurred locally on islands at the lagoon's edges where clay deposits could be excavated and where space existed for the kilns that fired raw bricks into finished building material. The clay was dug during summer when it was driest, mixed with water and sand to create proper consistency, formed in wooden moulds into standard brick sizes, and dried in the sun before being stacked in kilns where wood fires burned for days to vitrify the clay into hard ceramic. The brick-making industry employed specialized workers whose judgment determined quality. Too little firing left bricks that would crumble when exposed to weather. Too much created warped pieces unsuitable for construction. And the skill was knowing when the kiln had reached the correct temperature by observing flame color and listening to sounds the bricks made as they heated. Finished bricks were loaded onto flat-bottomed boats called birchi that could navigate the shallow lagoon channels. These boats carried hundreds of bricks stacked carefully to prevent breakage, and they delivered directly to construction sites where masons waited to incorporate them into walls, rising brick by brick toward their designed heights. Timber for structural frameworks came from mainland forests in the Veneto region, and from alpine valleys where rivers could float cut logs down to the coastal plain. Oak for heavy beams that would support floors and roofs, larch for secondary structural members, pine for scaffolding and temporary construction, and specialized woods like walnut for decorative elements and cabinetry. The timber trade involved multiple stages: foresters who selected and felled trees, sawyers who cut logs into beams at water-powered mills, rivermen who assembled log rafts and floated them downstream during spring floods when water levels were high enough for navigation, and the Venetian timber merchants who purchased the wood at coastal collection points and arranged its transport across the lagoon to the city. Long timbers presented particular challenges because they couldn't be maneuvered easily through the narrow canals. Specialized boats designed to carry beams up to 15 or 20 meters in length had to navigate carefully to avoid jamming in tight passages or damaging buildings along the route. Metal arrived as raw material to be worked by Venetian blacksmiths and foundries rather than as finished products. Iron ore from Alpine mines was smelted into bars at furnaces near the mining regions, where wood for fuel was abundant. These iron bars were shipped to Venice, where they were reheated and forged into the specific items construction required. Nails, brackets, chains, hinges, window frames, and the specialized clamps that held stone blocks together. Bronze and copper came from even more distant sources. Copper mines in Cyprus and other Mediterranean locations, tin from Cornwall in distant Britain to alloy with copper for bronze, and lead from various European sources for use in roofing and in the joints between stone blocks where it was poured molten to create flexible connections that allowed slight movement without cracking. The arsenal, Venice's massive shipyard complex, served not just for building the warships and merchant vessels that made Venice a maritime power, but also as the industrial centre where large-scale production provided materials and equipment for construction throughout the city. Rope was manufactured there from hemp fibre in quantities that supplied the entire construction industry with the cordage needed for lifting, binding and scaffolding work. The arsenal's rope walks, long covered buildings where fibre was twisted into progressively larger rope diameters, could produce rope up to 300 metres in length without splices, creating the continuous lines needed for hoisting materials from ships or for operating the pile drivers that continued driving foundations for new construction. The arsenal also produced the pulleys, blocks and hardware that made lifting systems functional, manufacturing these items with the precision that marine use demanded and that construction work benefited from through equipment that rarely failed under load. Transportation within Venice itself required a boat fleet numbering in the thousands. Small rowboats for moving individual workers or light loads, medium sandali for carrying several workers and their tools, larger cargo boats for delivering materials, and specialized vessels designed for particular cargoes like the stone-carrying boats with reinforced bottoms that could handle the weight and abrasion that stone transport inflicted. The boat builders formed guilds that passed skills across generations, building vessels specifically adapted to lagoon conditions, flat bottoms that could navigate shallow water, sharp prows that could push through the seaweed that choked some canals, and removable canopies that protected cargoes from rain while allowing clearance under the bridges that spanned the canals at heights that varied with the tides. What happens to construction logistics when the only available transportation route is water that rises and falls a metre or more with each tide cycle? The Venetians learned to time deliveries with tidal schedules. Boats loaded with heavy stone drew too much water to navigate the shallowest canals at low tide, so they waited for high water when depths increased enough for passage. But this meant construction sites might receive materials only during specific hours of each day, and work schedules had to accommodate the reality that deliveries couldn't be predicted with the precision that road transport allowed. Storage became critical. Materials needed to be moved off boats quickly because tying up waterfront space for extended periods disrupted traffic in canals that served as Venice's only streets, so construction sites developed stockpiling areas where delivered materials could be held until needed, though space limitations on the small islands meant that storage was always inadequate, and that just-in-time delivery before it had a name became necessary rather than optional. The economic cost of this water-based logistics system added substantially to construction expenses. Every stone block that would have been moved by cart on the mainland required boat transport in Venice. Every delivery needed workers skilled in handling boats rather than just loading and unloading, and delays caused by weather or tides meant that construction schedules stretched longer than comparable mainland projects. Yet the system worked because it had to. Venice had chosen to build in the lagoon, had committed to creating a great city despite the logistical challenges, and had developed over centuries the specialized trades, equipment, and knowledge that made construction possible even when every material arrived by boat and every building site was accessible only by water. The boats moving through the canals with their cargoes of stone and timber and brick represented not just transportation, but the bloodstream of a city that existed only because its people had learned to work with water instead of fighting against it, to use boats where others used carts, and to build magnificence despite barriers that would have convinced less determined communities to relocate somewhere simpler. Materials arriving by boat at construction sites needed to be transformed into walls, arches, roofs, and all the elements that buildings required. But this transformation happened through the hands of workers whose lives revolved around mastering techniques adapted specifically for lagoon conditions that made conventional construction methods inadequate or impossible. The masons who laid stone and brick faced challenges their mainland counterparts never encountered. Mortar mixed with fresh water wouldn't set properly in the damp, salt-laden environment, so they developed formulas incorporating volcanic ash called pozzolana that reacted chemically with lime to create cement that hardened even when wet, and that resisted the corrosive effects of salt that permeated everything in Venice. The bricklayers worked from boats or temporary platforms when building canal walls, balancing on narrow planks suspended above water, while laying courses that needed to be perfectly level despite having no stable ground to reference, relying on string lines and plumb bobs and the accumulated skill that came from years of experience working in conditions where a careless moment could mean falling into the canal below. The guild system that organised medieval labour throughout Europe took on particular importance in Venice, where specialised knowledge meant the difference between buildings that stood for centuries and structures that failed within years. The Arte dei Mureri governed stonemasons and bricklayers, establishing standards for mortar composition and brick quality, testing apprentices before allowing them to work independently, and maintaining the collective knowledge about which techniques succeeded in lagoon construction and which invariably led to problems. Membership in the Masons Guild required 7 years of apprenticeship, during which young workers learned not from books but from observation and practice, mixing mortar in the precise ratios that elders specified, cutting bricks to fit irregular spaces using nothing but a trowel edge and practiced eye, understanding by feel when mortar had reached the consistency that would bond properly, and developing the physical stamina that allowed working all day in positions that strained backs and shoulders and knees. How much did these construction workers earn for labour that combined skill with danger and exhaustion? The payment systems varied by trade and by the scale of projects. Ordinary labourers who move materials or mix mortar might receive enough for basic food and rent, but little more. Perhaps the equivalent of what could buy 4 or 5 kilograms of bread per day, barely sufficient for a family and leaving nothing for savings or emergencies. Skilled masons commanded significantly higher wages that reflected their years of training and the value they added to projects, perhaps double or triple what labourers earned, enough to support families with modest comfort and to accumulate some savings across years of steady employment. The master builders who designed projects and supervised construction could become wealthy by medieval standards. They negotiated contracts with churches and wealthy patrons. They employed teams of workers whose labour generated profit beyond their wages, and successful masters might own property and achieve social status that elevated them above the working class they had emerged from. The working conditions tested endurance in ways that varied with seasons and with the specific tasks being performed. Summer brought heat that made physical labour draining, that caused mortar to dry too quickly, requiring constant re-wetting to remain workable, and that created thirst that workers satisfied by drinking from canals whose water quality was questionable at best, and that contributed to the dysentery and other illnesses that periodically swept through work crews. Winter meant cold that made fingers stiff and clumsy, that turned wet clothing into freezing discomfort, that slowed mortar curing to the point where construction often paused for months, because walls built in winter might not set properly and would fail when loaded with the weight of additional stories planned above them. The workers had no protective equipment beyond perhaps leather gloves worn thin from use. They climbed scaffolding without harnesses, worked on roofs without railings, handled lime that burned skin if mortar splashed, and breathed stone dust that accumulated in lungs across decades of cutting and shaping blocks. The scaffolding systems that allowed workers to reach heights where walls were being built represented engineering challenges nearly as complex as the buildings themselves. Wooden poles lashed together with rope created frameworks that needed to support not just workers, but also the materials they were installing. The scaffolding had to be stable despite standing on ground that compressed slightly under load, and it needed to be assembled and disassembled as work progressed, since leaving permanent scaffolding in place would consume timber that Venice's limited resources couldn't spare. The scaffolding builders developed techniques for anchoring poles into masonry walls as construction rose. Wooden beams called pontarii were built into the wall itself, projecting outward a metre or so. Then vertical poles and horizontal platforms were lashed to these built-in anchors, creating working surfaces at each floor level. When construction reached completion, the pontarii were cut off flush with the wall surface and plastered over, but their sockets remained embedded in the masonry, where careful observers can still identify them in medieval Venetian buildings as regular patterns of holes or depressions in the brick and stone facades. What accidents befell workers during construction on unstable ground above water, where falls meant drowning as often as impact injuries? The records are incomplete because medieval employers rarely documented worker deaths with the precision modern historians would prefer, but contract disputes and occasional church records mention accidents that reveal the dangers. Masons falling from scaffolding when rope lashings failed, or when poles shifted under load, workers struck by falling stones when hoisting ropes broke or when load swung out of control, labourers crushed between boat and canal wall when delivering materials if timing misjudged the motion of both, and the drownings that occurred with grim regularity when workers who couldn't swim fell into canals and were pulled under by heavy clothing or tool belts before rescue could reach them. The guilds maintained funds to support widows and orphans of members killed in construction accidents. Modest payments that might cover funeral costs and provide temporary assistance, but that rarely sufficed for long-term support, leaving families to find other income through whatever work widows and children could perform. The salt corrosion problem that affected metal elements required constant attention from maintenance workers, whose labour represented ongoing costs throughout a building's life, rather than one-time construction expenses. Iron brackets holding stone blocks together began rusting almost immediately when exposed to Venice's salt-laden air. The rust expanded and created pressure that could crack stone if not addressed, and the solution involved coating metal with protective layers of lead or bronze that needed periodic renewal. The window frames, door hinges, decorative ironwork, and structural reinforcements All required inspection and treatment on schedules that property owners often neglected until visible damage forced expensive repairs. Some builders responded by minimizing metal use wherever possible, using wooden pegs instead of iron nails for certain applications, relying on careful stone fitting rather than metal clamps, accepting the limitations these choices imposed on architectural ambition in exchange for reduced maintenance demands. The plasterers who finished interior and exterior walls worked with lime-based plaster that incorporated marble dust to create surfaces called marmorino that could be polished to resemble marble at a fraction of the cost of actual stone facing. The technique involved applying multiple thin coats rather than single thick layers, burnishing each coat before adding the next, building up depth that created luminosity as light penetrated slightly into the translucent surface before reflecting back. The skilled plasterers developed sensitivity in their hands that allowed them to feel when the plaster had reached the precise stage for burnishing. Too early, and the surface would roughen. Too late, and it wouldn't polish. But at the correct moment, pressure from smooth stones or steel trowels compressed the surface into glass-like finish that needed no paint, because the marble dust provided colour and the polish provided protection. This specialized work commanded high wages because few workers mastered the technique sufficiently to produce results wealthy patrons demanded, and master plasterers might spend weeks on a single room creating surfaces that justified the premium they charged. The carpenters who built roof frameworks faced the challenge that wooden structures inevitably moved slightly as humidity changed, and as the building settled on their piling foundations. Rigid connections would crack as movement occurred, so Venetian carpenters developed joinery systems that allowed controlled flexibility, using mortise and tenon joints that could shift slightly without failing, avoiding nails in favor of wooden pegs that compressed rather than shearing when stressed, and designing roof trusses that distributed loads through multiple members so that failure of any single piece wouldn't cause collapse. The chestnut wood commonly used for roof framing contained natural oils that resisted insect damage and that slowed decay even when moisture penetrated through failed roof tiles. Buildings several centuries old often retained original roof frameworks that remained sound enough to support renovations that replaced everything else. Living conditions for construction workers reflected the same space constraints that affected all Venetian residents. Housing consisted typically of rooms in multi-story buildings where entire families occupied single spaces that served as sleeping, cooking, and living areas with no separation. Windows were small openings that could be shuttered against weather, but that provided limited light and ventilation. Sanitation meant chamber pots emptied into canals that tidal action was supposed to flush twice daily, but that in reality accumulated waste in areas where water circulation was poor. Workers might walk 30 minutes or more from their housing to construction sites, because only the wealthy could afford to live near the city centre, where major building projects occurred. The walking happened along narrow calli, where two people could barely pass side by side, across bridges whose steps challenged those carrying tools, through areas that flooded during Aqua Alta, when high tides combined with weather to push water above the normal canal levels and into the streets and ground floors of buildings. The food that sustained workers through physical labour came from markets supplied by boats, bringing produce from mainland farms, fish caught in the lagoon and Adriatic, and grain shipped from distant sources because Venice's islands couldn't grow crops beyond small garden plots, Workers ate bread as their primary calorie source, fish when affordable, supplemented by occasional meat, vegetables in season but preserved foods during winter, all prepared in home kitchens that consisted of simple hearths for cooking and limited storage for ingredients that needed to be purchased fresh because preservation methods were unreliable. The cost of food consumed much of a worker's wages, leaving little for anything beyond survival necessities, making illness or injury catastrophic because missing work meant families went hungry, and creating the poverty that drove workers to accept dangerous construction jobs because alternatives were worse or non-existent. By the 14th century, when Venice reached its peak as a Mediterranean power, the construction workforce had developed into a sophisticated system where specialized trades intersected to create buildings of remarkable quality. Despite the challenges that lagoon location imposed, the masons and carpenters and plasterers and scaffolders and all the other workers whose individual skills combined into collective capability to build churches and palaces understood that their labor was creating something permanent, that the difficulties they endured and the skills they mastered were making possible a city that would outlast them by centuries, and that the wages earned through months and years of exhausting work allowed survival in a place where merely living represented achievement, given the odds against human habitation that the lagoon's unstable ground and encroaching water presented to every generation that chose to remain rather than retreat to the easier existence that solid mainland Earth offered just beyond the horizon. The buildings rising on their wooden foundations needed connections to each other and to the wider city, but conventional streets paved with stone and designed for wheeled traffic couldn't exist in Venice, where the ground was too soft to support such infrastructure, and where water already filled the spaces between islands that nature had created when the lagoon formed. The Venetians accepted what the lagoon's geography offered and shaped it into deliberate design. The natural channels where water flowed with the tides became formalized canals with defined edges. The deeper waterways were maintained through dredging to allow boat traffic even at low tide, and the entire network was gradually refined across centuries until Venice possessed roughly 150 canals that served simultaneously as streets for transportation, as sewers for waste disposal, and as foundations for the city's identity as a place fundamentally different from anywhere else humans had built. The canal creation didn't involve excavating through dry ground, but rather defining and deepening channels that already existed as tidal flows. Survey teams working from boats used weighted lines to measure water depth at low tide, identifying which natural channels could be developed into reliable navigation routes and which areas were too shallow for anything except small boats or passage only during high water. The dredging work that deepened canals employed specialized workers called fangatori, whose labor consisted of scooping mud from canal bottoms using long-handled tools while standing in shallow boats designed specifically for this purpose. The boats called burchiel had flat bottoms that allowed them to rest on the canal bed at low tide without tipping, giving workers stable platforms from which to work during the hours when water levels dropped enough to expose the mud that needed removal. How do you dispose of tons of mud dredged from canals when there's no open land nearby for dumping? The solution involved using the mud as fill material to raise the elevation of island edges and create new building plots. The dredged material was transported to areas selected for development, spread across the surface to depths of 1 meter or more, and allowed to dry and consolidate over periods of months or years until it became stable enough to drive pilings through for new construction. This process gradually expanded Venice's usable land area. Islands that had been barely above water level at high tide became raised enough to remain dry except during the worst flooding, and entirely new islands were created in areas that had been open water by repeatedly depositing dredged mud until accumulation built up to elevations that pilings could be driven into to create foundations for buildings. The canal walls, called fondamenta, that defined the edges and prevented erosion, required construction techniques that combined wooden piling foundations with stone facing to create stable vertical surfaces that could withstand the constant pressure of tidal water moving in and out twice daily. Pilings were driven along the desired canal edge line at spacing close enough that horizontal planks could be attached between them to create a wall that held back the mudfill behind. Then Istrian stone blocks were set against this wooden wall to create the visible surface that boats would tie against and that would resist the wear from ropes and the impact from vessels manoeuvring in tight spaces. The stone blocks were fitted carefully so that gaps were minimal. Wide spaces would allow water pressure to wash out the mudfill behind the wall and undermine the stability that the entire system depended upon. The maintenance of these canal walls represented ongoing work that required constant vigilance. Inspectors employed by the city government checked regularly for signs of failure, such as bulging stones that indicated pressure building behind the wall, gaps opening between blocks that suggested settlement was occurring, or wooden pilings at water level showing rot that meant they needed replacement before structural failure occurred. The repairs involved partially dismantling damaged sections, driving new pilings if the originals had failed, rebuilding the stone facing, and often injecting additional fill material behind the wall to replace what had washed out through gaps before the damage was detected. The cost of this maintenance was distributed across property owners whose buildings fronted the canals. Each owner was responsible for the fondamenta section adjacent to their property, creating incentives for prompt repairs since failure affected not just the canal wall, but potentially the building's foundation stability. What happens to human waste and household garbage in a city where canals serve as streets and where tidal action is expected to flush everything away? The Venetian sanitation system relied on the twice-daily tidal cycle that brought fresh seawater in from the Adriatic during rising tide and carried water back out during the ebb. Privies in buildings emptied directly into canals through pipes or chutes. Kitchen waste was thrown into the water, and the assumption was that tidal flows would carry everything out to sea before accumulation became problematic. The system worked imperfectly. Canals with poor water circulation accumulated waste that created health hazards and offensive smells. Dead zones developed in areas where tidal exchange was minimal, and during summer, when the Adriatic's tidal range decreased, the flushing action weakened enough that visible waste floated in canals and diseases spread through populations drinking water or eating food, contaminated by the inadequate sanitation. The city government attempted to regulate the worst problems through laws prohibiting certain activities. Ordinances forbade dumping animal carcasses or tannery waste into canals, restricted where butchers could discard offal, and required that some types of industrial waste be transported by boat to disposal sites outside the city rather than released into local canals. Enforcement was inconsistent because monitoring every canal constantly exceeded the government's capacity, and because economic pressures meant that businesses and residents often violated regulations when the immediate convenience of dumping waste nearby outweighed the abstract long-term consequences of contaminating the water that surrounded them. The wealthy who could afford houses on the Grand Canal or on other main waterways with strong tidal flow suffered less from sanitation problems than those living on narrow side canals, where water barely moved and where waste accumulated despite the tide's theoretical cleansing action. The drinking water supply presented challenges distinct from the sewage problems. The lagoon water itself was brackish and undrinkable, mixing seawater with fresh water from mainland rivers in proportions that varied with tides and seasons, but that never produced water suitable for consumption. Venice addressed this through elaborate systems of rainwater collection, where roof surfaces channeled precipitation into underground cisterns called pozzi that filtered the water through sand layers before storage in sealed chambers, where it remained cool and protected from contamination. Each neighbourhood had several public wells connected to these cisterns. The wells were marked by distinctive stone well heads carved with decorations that identified which wealthy patron had funded their construction, and residents drew water daily using buckets and ropes in rituals that created social gathering points, where news and gossip circulated along with the water that sustained life. How much water does a city of tens of thousands of people require daily when there are no rivers or springs to supply it? The cistern system represented massive infrastructure investment. Each cistern required excavation down to levels below the normal water table, installation of clay linings to prevent the collected rainwater from draining away into the surrounding saturated ground, the sand filtering layers that removed sediment and some contaminants from the roof runoff, and the brick or stone chambers that held the filtered water until drawn through the wells. A typical neighbourhood cistern might store 50,000 to 100,000 litres, enough to supply surrounding residents for weeks if rain failed. And the city maintained hundreds of these cisterns with constant attention to preventing contamination and repairing damage that earthquakes or settlement might cause to the underground structures. During prolonged droughts, when cisterns ran low, water was imported from the mainland by boat. Specialized vessels with sealed holds transported fresh water from rivers to Venice, where it was sold at premium prices that reflected the labor and risk involved in the transport. And the water sellers became important figures in neighborhoods where cisterns had failed or where populations exceeded the capacity of existing collection systems. The need for imported water created vulnerabilities. Military sieges could attempt to cut off water supplies along with food, and the city invested in expanding cistern capacity specifically to reduce dependence on mainland sources that enemies might interdict during conflicts. The flood management problem that would eventually threaten Venice's survival began manifesting during medieval times as aqua alta events, when combinations of high tides, strong winds, and low atmospheric pressure pushed water levels above normal maximums and flooded ground floors of buildings in the lower-lying Campo squares, where markets and community activities occurred. The early floods were considered nuisances rather than catastrophes. Water retreated within hours as tides dropped, and the primary impact was temporary disruption and water damage to goods stored at ground level. Property owners responded by raising floor levels in ground floor rooms, by moving valuable storage to upper floors, and by installing removable barriers across doorways that could be fitted into place when flooding threatened, based on predictions that experienced observers could make by watching tide patterns and weather conditions. The drainage from higher ground into the canals required careful design to prevent erosion that could undermine building foundations. Rainwater running off roofs and paved surfaces was channeled through downspouts and gutters that directed it into canals at controlled points, rather than allowing it to cascade randomly down walls where it might wash away mortar or erode the mud fill behind fundamental walls. The bridges that cross canals were designed with drainage channels built into their structure so that water crossing the bridge surface didn't accumulate but flowed through openings into the canal below. This prevented water weight from stressing the bridge foundations and ensured that heavy rains didn't create flooding on the bridges themselves that would make them impassable. By the Renaissance period, when Venice had matured into the physical form that tourists would eventually recognize as quintessentially Venetian, the canal network had become so integral to city function that proposals to fill certain canals and create conventional streets were rejected, not just for the enormous costs such projects would entail, but because Venetians had come to understand their city as fundamentally aquatic. The canals weren't obstacles to be overcome, but rather features to be celebrated and maintained. They defined Venice's character and its competitive advantage as a port city, where ships could penetrate deep into the urban fabric, rather than stopping at harbour edges as they did in mainland cities. The water that surrounded every building and that flowed through every neighbourhood represented both challenge and opportunity. It required constant vigilance and maintenance. It created health hazards and flooding problems. But it also provided transportation efficiency, defensive advantages, and the unique identity that made Venice memorable across centuries, when dozens of medieval Italian cities competed for trade and influence. But only one could claim to be the city that floated on water, where water itself became the foundation for everything humans built upon it. The canals that served as Venice's streets created the necessity for bridges that allowed pedestrian movement between islands without requiring boats for every crossing. Yet building permanent spans over water channels in a city where conventional foundations couldn't exist presented engineering challenges that required innovations distinct from mainland bridge construction, where stable ground anchored both ends and where builders could work from dry riverbeds during construction. The earliest Venetian bridges were simple wooden structures, planks laid across beams supported by wooden pilings driven into the canal beds, flat surfaces without railings that allowed people and handcarts to cross, but that required replacement every few decades as the wood deteriorated from exposure to air and water alternately, and that posed hazards during rain when wet planks became slippery, and when flooding raised water levels high enough that the flat bridges became submerged and invisible to anyone attempting to cross. The transition from wood to stone bridges began in the 15th century, as Venice's wealth from maritime trade provided resources for permanent infrastructure, and as masonry techniques developed sufficiently that builders could construct arched spans capable of crossing canal widths, while remaining high enough above the water that boats could pass beneath even at high tide. The stone bridges required foundations at both ends that were themselves substantial construction projects. Wooden pilings were driven in dense clusters at the canal banks to create foundation platforms. These platforms were capped with Istrian stone layers just as building foundations were, and then the bridge abutments were built up from these foundations using brick and stone masonry that needed to be thick enough to resist the horizontal thrust that arch bridges exerted outward on their supports. How do you construct a stone arch over water when there's no dry ground to build temporary scaffolding from? and when boat traffic needs to continue using the canal during the months or years that bridge construction requires. The builders developed techniques using wooden centering structures that were assembled on boats and then positioned carefully in the canal to provide the curved framework that would support stone blocks during arch construction. The centering consisted of wooden ribs cut to the precise curve the finished arch would follow. These ribs were braced together and supported by vertical posts that rested on the canal bottom or on piles, driven specifically for the temporary support they would provide during construction. The boats that positioned the centering had to account for tidal variations. What fit perfectly at low tide might jam against canal walls at high water, and the entire structure needed to remain stable despite the rising and falling water levels that occurred throughout each day. The stone blocks forming the arch were cut at workshops on land where masons could work with precision tools and stable surfaces. Each block was shaped as a wedge called a voussoir, with its inner surface smaller than its outer surface, so that when multiple blocks were assembled in sequence they formed the curve, and the dimensions had to be calculated so that all the blocks together would create an arch of exactly the span needed to cross from one abutment to the other. The blocks were transported by boat to the construction site and lifted into position on the wooden centering using rope and pulley systems, starting from both ends and working toward the center, where the final keystone would be placed to lock the arch together, and each block was mortared to its neighbors using the pozzolana lime mixture that would cure even in the damp conditions that characterized all Venetian construction. The Rialto Bridge, constructed between 1588 and 1591 to replace earlier wooden bridges that had repeatedly failed or burned, represented the peak achievement of Venetian bridge engineering and became one of the city's most recognizable landmarks. Designed by Antonio da Ponte, whose name meant Anthony of the Bridge, in convenient coincidence, the structure consists of a single stone arch spanning 28 meters across the Grand Canal at one of its narrower points where the canal makes a gentle curve. The arch itself is relatively shallow. Its rise from the water surface to the crown is only about 7 meters, creating what engineers call a segmental arch, where the curve is less than a full semicircle, and this shallow profile was chosen both for aesthetic reasons and because a higher arch would have required more extensive abutment foundations to resist the increased horizontal thrust that steeper arches generate. What makes a bridge built in 1591 still carrying pedestrian traffic more than 4 centuries later without major structural repairs or reinforcement? The engineering incorporated redundancy and careful load distribution. The main arch that spans the canal is supplemented by 2 smaller arches at each end that reduce the structure's weight while maintaining strength. The walkway across the bridge includes 2 rows of shops built into the structure itself, adding weight that helps stabilize the arch rather than creating additional burden, and the foundations extend deep into the canal bed on both banks, with pilings driven until they reached clay, dense enough to resist the enormous forces the arch abutments transmit downward and outward. The stone used for the Rialto's visible surfaces is Istrian limestone, chosen for its resistance to weathering and its strength under compression, while the internal structure uses brick extensively because brick was cheaper than stone and because the combination of materials allowed builders to balance cost against performance requirements. The Bridge of Sighs, constructed in 1600 to connect the Doge's palace with the new prison across a narrow canal, took an entirely different form as an enclosed structure rather than an open span. The bridge consists of two parallel stone arch passages enclosed by walls with windows, creating what is essentially a building suspended over water rather than a traditional open bridge. The name Bridge of Sighs came from Romantic tradition, suggesting that prisoners crossing from the interrogation rooms to their cells would sigh at their last view of Venice through the bridge windows, though historical evidence suggests the reality was less poetic and that most prisoners using the bridge were minor offenders rather than condemned men seeing freedom for the last time. The enclosed design required substantial foundations at both ends, where the bridge attached to existing buildings. The connections needed to distribute the bridge's weight into the palace and prison walls without creating stress concentrations that might crack the masonry. The smaller bridges that numbered in the hundreds throughout Venice varied enormously in design and quality. Some were substantial stone arches built with the same care as major bridges like the Rialto, funded by wealthy patrons or by neighborhood associations that raised money through contributions and that hired competent builders who followed established techniques. Others were makeshift structures thrown up quickly to connect newly developed areas, built by less skilled workers using whatever materials were available cheaply. And these inferior bridges required constant maintenance and frequent replacement when they deteriorated beyond repair or when they simply collapsed under load or storm damage. The city government attempted to regulate bridge construction through ordinances requiring that designs be approved and that construction meet minimum standards, but enforcement was difficult and many bridges were built without permission by property owners who valued convenience over regulation. The steps that characterize nearly all Venetian bridges created both functionality and problems. The steps allowed the bridge crown to reach sufficient height that boats could pass underneath, while keeping the approach ramps from extending too far into the limited space available on the small islands. But the steps made crossing with handcarts extremely difficult, since wheels couldn't roll up stairs and everything had to be carried by human labor. Some bridges incorporated side ramps with gentle slopes specifically for carts, but these required even more space than stepped approaches and were feasible only at larger bridges where adequate room existed. The elderly and infirm found the bridges challenging. Venice's terrain meant that simply moving around the city required constantly climbing and descending bridge steps, and those with mobility limitations might find entire sections of the city effectively inaccessible because reaching them required crossing bridges their physical condition wouldn't allow. The railings that eventually became standard features on Venetian bridges were absent from earlier structures where the walkway simply ended at its edges with no barrier preventing pedestrians from falling into the canal. The absence of railings reflected both the cost of including them and the medieval attitude that people were responsible for their own safety, and that falling off a bridge indicated carelessness rather than inadequate design. As bridges became busier with increased traffic, and as social attitudes shifted toward expecting public infrastructure to provide safety features, railings were added to existing bridges and incorporated into new construction as standard elements. Stone balustrades on major bridges, simpler iron or wooden rails on minor spans, all designed to prevent accidental falls, while allowing people to lean over and observe the canal traffic passing below. The maintenance of Venice's bridge network required continuous expenditure. Stone surfaces worn smooth by centuries of foot traffic needed periodic resurfacing to prevent them from becoming dangerously slippery when wet. Mortar joints between stones deteriorated from salt exposure, and needed repointing to prevent water infiltration that would cause freeze-thaw damage during winter, and the foundations needed monitoring for signs of settlement or movement that might indicate the wooden pilings beneath were finally failing after decades or centuries of supporting the bridge weight. Some bridges settled slightly over time as the ground beneath their abutments compressed, creating humps or dips in the walking surface that were corrected by adding stone shims or by rebuilding sections to restore the original profile. By the 18th century, when Venice had largely completed its physical development, and when the city's political and economic power was declining from its medieval peak, the bridges had become such defining features of the urban landscape that artists incorporated them into paintings and prints that circulated throughout Europe. Visitors commented on the experience of constantly crossing bridges to move through the city, on the distinctive architecture that the necessity of spanning canals had created, and on the way Venice's bridges served simultaneously as practical infrastructure and as romantic settings where meetings occurred and where views across the canals provided vistas impossible in conventional cities. The bridges represented accumulated engineering knowledge translated into stone and mortar. Each arch had been calculated, even if only through practical experience, rather than mathematical formulas. Each foundation had been built with awareness that failure meant not just reconstruction costs, but potential loss of life if collapse occurred when people were crossing, and each structure testified to the determination of Venetians to create permanent connections across water that geography would otherwise have left as barriers requiring boats for every crossing. The bridges connected islands and the canals provided transportation routes, but Venice needed monumental architecture that would proclaim its wealth, express its political power, house its religious life, and demonstrate that a city built on wooden stakes in a lagoon could achieve magnificence rivaling anything mainland Europe produced. These ambitions materialized in structures like St. Mark's Basilica, with its Byzantine domes gleaming with gold mosaics, the Doge's Palace, where Venice's elected leader governed from rooms decorated with masterworks by the greatest painters of the age, and the Arsenal shipyard, where industrial-scale production turned out warships and merchant vessels with efficiency that made Venice the Mediterranean's dominant maritime force for centuries. St. Mark's Basilica began construction in 1063 to replace an earlier church on the same site near what would become the symbolic heart of Venice. The building was designed deliberately to evoke Constantinople's great churches with its Greek cross plan and its multiple domes, a statement that Venice considered itself heir to Byzantine civilization and equal to any power in Christendom, despite being built in a swamp that more established cities dismissed as unsuitable for serious habitation. The foundation work required driving thousands of wooden pilings into the mud of St. Mark's Square to create a platform capable of supporting not just the church's stone walls, but also the enormous weight of the 5 brick domes that would crown the structure. Each dome required internal timber frameworks during construction to hold the shape while the brick and mortar cured, and the completed domes transferred their weight down through pendentives, triangular sections that transitioned from the circular dome base to the square walls below, into massive piers that stood on the densest piling arrays builders could create. How do you construct brick domes spanning 13 meters in diameter when the slightest settlement would crack the thin shell and potentially cause catastrophic collapse? The builders employed techniques learned from Byzantine predecessors. The dome bricks were laid in horizontal rings starting from the base and spiraling upward toward the crown. Each ring was slightly smaller in diameter than the one below, and the bricks were set in thick mortar beds that allowed some flexibility as the structure settled onto its foundations during the months following construction. The domes were built as double shells with a gap between the inner and outer layers. This reduced weight compared to solid domes while providing space where timber reinforcement could be hidden, and the double shell system allowed the external profile to differ from the internal curve, giving builders flexibility to create the onion-shaped external appearance that characterized Byzantine architecture, while maintaining the structural efficiency of a more hemispherical inner dome. The interior decoration of St. Mark's consumed decades beyond the basic structural completion. More than 8,000 square meters of gold-backed glass mosaic covers the walls, ceilings, and domes, creating glowing surfaces that shimmer in candlelight and that depict biblical scenes in artistic styles blending Western and Eastern Christian traditions. The mosaic work required specialized craftsmen called mosaicisti, who set tiny glass tesserae, cubes typically 5 to 10 millimeters on a side, into wet plaster following designs drawn on the wall surface by master artists. The tesserae were tilted at slight angles rather than set perfectly flat, so that light reflecting off the irregular surface created the shimmer that made the mosaics appear to move and glow, and the gold backing was created by sandwiching. Gold leaf between layers of clear glass protecting the precious metal while allowing it to reflect light. The cost of these mosaics was staggering. Materials alone consumed budgets that could have built entire churches, and the labour of craftsmen working for years to cover every available surface made St. Mark's one of the most expensive buildings constructed during the medieval period anywhere in Europe. The Doge's Palace, constructed primarily during the 14th and 15th centuries on a site adjacent to St. Mark's Basilica, served as both the residence of Venice's elected leader and the administrative centre where councils met to govern the Republic. The building's distinctive appearance, with its pink and white patterned marble facade sitting atop an arcade of Gothic arches, created an architectural statement that appeared almost top-heavy, with the solid upper stories resting on what looked like delicate colonnade supports. The visual impression defied conventional architectural hierarchies, where heavy elements belonged at the bottom and lighter elements above, but the structure was engineered carefully to distribute loads. The arcade columns were substantial despite their graceful appearance. The foundations beneath them extended deep into the ground on particularly dense piling arrays, and the walls above were actually less heavy than they appeared, because much of the facade's thickness was hollow cavity rather than solid masonry. What political statement does architecture make when a government chooses to build a palace that appears delicate rather than fortress-like? The Doge's palace design reflected Venetian republican ideology that distinguished their system from the hereditary monarchies ruling most of Europe. Venice's leaders were elected and accountable to councils of nobles rather than inheriting power through royal bloodlines, and the palace's openness with its ground floor arcade allowing public access to the square rather than presenting defensive walls suggested a government confident in its legitimacy and unafraid of its citizens. The interior spaces included council chambers where hundreds of nobles gathered to debate policy, offices for the bureaucracy that administered Venice's territories and trade networks, armories for weapons storage, and prison cells in upper floors where political prisoners were held before the Bridge of Sighs was built to connect to the separate prison building. The decorative program inside the palace featured paintings by Venice's greatest artists. Tintoretto's enormous paradise, covering an entire wall of the great council chamber, depicted heaven populated by hundreds of figures and representing, at the time it was painted, the largest canvas ever created. Veronesi's ceiling paintings allegorizing Venice's virtues as a republic, and countless other works commissioned specifically for rooms where they would impress visitors and remind Venetian officials of the Republic's glorious history and divine favour. The paintings required special mounting systems because conventional frames and attachments might not hold in buildings that move slightly on their piling foundations. The canvases were often built into the architecture itself during construction or renovation, creating integrated decoration that became part of the building structure, rather than removable artworks that later generations might strip away. The Arsenal represented an entirely different type of monumental construction, focused on industrial production rather than aesthetic display or political symbolism. Established by the early 12th century and expanded repeatedly until it covered nearly 45 hectares, the Arsenal was essentially a state-owned shipbuilding complex where Venice constructed and maintained the galleys that protected its trade routes and projected military power throughout the Mediterranean. The facility was surrounded by fortified walls that protected both the valuable ships under construction and the military technologies that gave Venetian vessels advantages over competitors. The walls incorporated towers for defensive positions, gates that could be sealed to prevent unauthorized access, and canals that connected the interior basins where ships were built to the lagoon channels that allowed completed vessels to be launched into service. The Arsenal's revolutionary aspect was its organization of labor into something resembling a modern assembly line centuries before the Industrial Revolution. Rather than building each ship from start to finish in one location with a single crew doing all the work, the Arsenal divided construction into stages that occurred at different stations as the hull moved through the facility. Specialized teams installed ribs, others planked the hull, different workers stepped the masts, riggers attached the standing and running rigging, and craftsmen installed fittings and weapons. This specialization allowed workers to become extremely efficient at their particular tasks, and it meant that during emergencies Venice could produce completed galleys in time frames that foreign observers found unbelievable. Historical accounts describe instances where a galley was framed, planked, rigged, and launched in a single day when war required rapid fleet expansion. Whether this was typical or whether it represented propaganda exaggeration remains debated, but even skeptical historians acknowledge that Arsenal production rates far exceeded what traditional shipbuilding methods achieved. At its peak, the Arsenal employed more than 16,000 workers called Arsenalotti, who formed a distinct social class within Venice. They received steady wages from the government rather than working for private contractors whose employment fluctuated with available commissions. They had access to guild benefits, including modest pensions for those who worked long enough to qualify, and they constituted a pool of skilled maritime labour that Venice could mobilize for military campaigns or for emergency repairs when trading vessels required service. The Arsenalotti developed strong corporate identity. They marched as a unit in civic processions. They had distinctive clothing that identified their status, and they served as informal enforcers of public order, since their numbers and organization made them a force that even unruly nobles hesitated to provoke. The rope manufacturing that supported shipbuilding occurred in long buildings called rope walks, where hemp fibers were twisted into progressively larger diameter cordage. A ship required miles of rope in various sizes, from thin lines for light duty to massive cables for anchors and for towing, and the arsenal produced this rope in-house, rather than depending on outside suppliers whose quality might be inconsistent. The rope walks were among the longest buildings in medieval Europe. Some exceeded 300 meters in length to allow continuous rope production, without splices that would create weak points, and the building's distinctive narrow proportions made them easily identifiable in views of the arsenal complex. Workers walked backward down the length of the building while twisting fibers together, their pace and technique determined by experience and by the specifications for the particular rope diameter being produced. The dry docks, where ships could be hauled out of water for hull maintenance and repairs, represented significant engineering achievements. Excavations were dug below the normal water level, with gates that could be opened to allow ships to enter when the dock was flooded. Then the gates were closed and the water was pumped out using systems of Archimedean screws or chain pumps driven by human labour on treadmills, lowering the water level gradually until the ship rested on blocks and the hull was accessible for work. The pumping required to empty a dock consumed enormous labour. Keeping ahead of the water that seeped through the gates and that infiltrated through the dock walls from the surrounding lagoon meant that pumping crews worked constantly during the days or weeks that a ship occupied a dry dock. And the cost of this labour made dock time expensive enough that ship captains scheduled hull cleaning and repairs carefully to minimise the time out of service. By the 16th century, when Venice reached its maximum territorial extent, and when its maritime dominance faced increasing challenges from Atlantic powers like Spain and Portugal, the combination of St. Mark's religious splendour, the Doge's palace political theatre, and the Arsenal industrial might created an urban ensemble that proclaimed Venice's unique character. Here was a city that had transformed impossible swampland into one of Europe's great powers through engineering that created foundations where none existed, through trade networks that connected east and west, through governmental systems that balanced competing interests, and through sheer determination that refused to accept that some places were too difficult for human ambition to overcome. The monuments that Venice built across centuries to demonstrate its permanence carried within them a troubling reality that became increasingly apparent as the city aged. The wooden pilings and soft substrate that had allowed construction on the lagoon also meant that everything built in Venice was slowly sinking as the mud beneath compressed under sustained weight, as the wooden poles gradually degraded despite their underwater preservation, and as the very success that had created a dense urban environment added mass that the foundation struggled to support across generations. The sinking occurred at rates too gradual for any individual to perceive, perhaps 1 or 2 millimeters per year on average, barely measurable without precision instruments, but accumulating across decades and centuries into subsidence that could be measured in centimeters, and eventually in tens of centimeters, that transformed building relationships with the water surrounding them, and that made structures designed with ground floors well above normal tides increasingly vulnerable to flooding that earlier generations had never experienced. The aqua alta, high water, that periodically pushed lagoon levels above normal maximums and flooded the lower-lying areas of Venice had occurred since the city's founding, but historical records suggest that the frequency and severity increased dramatically across the 20th century as multiple factors combined to worsen the flooding problem beyond what natural tidal variations alone would create. The moon's gravitational pull and the atmospheric pressure systems that drove normal tides continued operating as they always had. But Venice itself was sinking faster than before due to groundwater extraction that had accelerated during the early and mid-20th century when industrial facilities on the lagoon's edges pumped water from underground aquifers for manufacturing processes. Removing this water caused the ground to compact as the spaces previously filled with water collapsed, and this compaction occurred not just beneath the pumping sites, but throughout the interconnected substrate, including beneath Venice's historic centre, where no pumping was happening but where the effect propagated through the geological layers. How much can a city sink before the relationship between buildings and water shifts from manageable inconvenience to existential threat? By the 1960s, Venice had subsided roughly 23 centimetres compared to its elevation a century earlier. This meant that events which would previously have caused minor flooding in the lowest areas now inundated much larger portions of the city, and extreme high tides that had once been rare curiosities occurred with disturbing regularity. St. Mark's Square, which sits at one of the lowest elevations in Venice because it was built on filled marsh rather than on a natural island, became a reliable indicator of flooding. When Acqua Alta reached sufficient levels, the square transformed into a shallow lake, where tourists photographed each other wading through water that lapped against the basilica's entrance and that entered ground floor shops and businesses, causing damage that repeated floods multiplied into substantial economic losses. The catastrophic flood of November 1966 finally forced recognition that Venice faced challenges requiring intervention beyond what traditional maintenance and adaptation could address. A combination of exceptionally high tides, strong sirocco winds from the south that pushed water into the lagoon faster than it could drain out, and low atmospheric pressure that raised sea levels created a storm surge that peaked at 194 centimetres above normal sea level. The water invaded ground floors throughout the city, submerged St. Mark's Square under more than a metre of water, damaged artworks and historical artefacts that had survived centuries, only to be destroyed by saltwater immersion, flooded the oil storage tanks at the industrial port, causing petroleum contamination that spread through the floodwaters and killed several people either directly through drowning or indirectly through accidents related to the emergency conditions. The aftermath of the 1966 flood included international outcry and the first serious proposals for engineering interventions that might protect Venice from future disasters. The debate about how to save Venice consumed decades as engineers proposed solutions ranging from modest interventions like raising walkways and building barriers around critical areas to radical schemes that would have fundamentally altered the lagoon's hydrology by closing off some tidal inlets or by constructing massive seawalls that would separate the lagoon from the Adriatic entirely. The challenge was that any intervention that prevented tidal flooding might also disrupt the delicate balance that made the lagoon a functioning ecosystem. The twice-daily tidal exchange brought in oxygenated seawater and flushed out pollutants, and blocking this exchange could turn the lagoon into a stagnant dead zone where algae blooms consumed oxygen and where the water quality that already barely supported marine life would deteriorate to complete toxicity. What solution could protect the city from storms while preserving the tidal flows that centuries of adaptation had made Venice dependent upon? The MOSE project, an Italian acronym meaning Experimental Electromechanical Module, that also referenced the biblical Moses who parted seas, represented the compromise that eventually gained approval after years of political debate, environmental reviews, cost revisions, and engineering refinements. The system consists of mobile barriers installed at the three inlets. Where the lagoon connects to the Adriatic Sea, the barriers normally rest flat on the seabed in concrete housings, allowing tidal flows to continue unchanged. But when forecasts predict aqua alta events above threshold levels, compressed air is pumped into the hollow steel barriers, causing them to rotate upward on hinges until they form temporary dams that block water from entering the lagoon during the high tide peak. After the storm surge passes, the barriers are filled with water again and sink back to their resting positions, allowing normal tidal exchange to resume. Construction of the Meuse barriers began in 2003 after decades of planning and debate about whether the project was necessary, whether the design would work as predicted, whether the environmental impacts were acceptable, and whether the enormous cost, eventually exceeding €5 billion, could be justified when the same funds might address other urgent needs in Italy's chronically underfunded infrastructure systems. The construction involved underwater work at the three lagoon inlets, excavating trenches in the seabed to create the housings where the barriers would rest, building concrete structures that needed to withstand marine conditions and that needed to function reliably despite being submerged for years with only occasional activation, installing the massive steel gates that each measured roughly 20 meters wide and 30 meters long and weighed approximately 300 tons, and creating the complex mechanical and electrical systems that would control activation during storm events. What delays a project designed to save a city from drowning until nearly 2 decades pass between groundbreaking and first operational use? The Meuse construction suffered from multiple problems that became Italian political scandals. Cost overruns multiplied as engineering challenges proved more difficult than initial estimates suggested. Corruption investigations revealed that contractors and public officials had embezzled funds through bid rigging and false billing schemes. Technical problems emerged, with some components requiring redesign and replacement before the system could be trusted for actual emergency deployment, and environmental concerns about impacts on marine life and lagoon ecology required mitigation measures that added complexity and expense. The project became a symbol of Italian infrastructure dysfunction, a technically sophisticated solution that should have protected Venice years earlier, but that remained incomplete while politicians argued, and while investigators pursued corruption cases that eventually resulted in arrests and convictions, but that did nothing to accelerate the construction timeline. The first successful test deployment of the Meuse barriers occurred in October 2020. 78 individual barriers at the three inlets rotated up from their seabed positions and successfully blocked an aqua alta event that would have flooded portions of Venice, demonstrating that the engineering fundamentally worked even if the project had consumed far more time and money than anyone had projected when construction began 17 years earlier. The activation prevented flooding that would have caused tens of millions of euros in damage, and that would have disrupted life for thousands of Venetians who had lived with increasing flood frequency as climate change and sea level rise made high tide events both more common and more severe. Subsequent activations during the 2020-2021 winter confirmed that the system could be operated reliably when needed, though concerns remained about long-term maintenance costs and about whether the barriers could continue protecting Venice as sea levels rose beyond the roughly half-meter increase the system was designed to accommodate. Beyond the Meuse barriers, Venice's preservation requires addressing subsidence through measures that reverse the practices causing the most rapid sinking. Groundwater extraction from beneath the lagoon was prohibited in the 1970s, allowing the aquifers to gradually recharge and reducing the compaction that had accelerated sinking during the mid-20th century. The ban on groundwater pumping, combined with restrictions on industrial development in the lagoon area, has slowed subsidence to rates closer to the natural geological settling that would occur anyway as the mud beneath Venice continues its millennia-long compression under the weight of buildings above. Monitoring systems using GPS and other precision instruments track movements at hundreds of locations throughout the city, providing data that allows early detection of areas where settling exceeds normal rates and where foundation problems might require intervention before structural damage occurs. The cost of maintaining Venice extends far beyond the Meuse system into continuous work repairing foundations, replacing deteriorated pilings, cleaning canals, maintaining buildings whose ages measure in centuries, and adapting a medieval urban fabric to contemporary needs that include accommodating millions of tourists annually, while trying to maintain residential populations that can sustain the city as a living community rather than an outdoor museum. The human cost that built Venice included the unknown thousands who died during construction across 15 centuries, workers who fell from scaffolding or drowned in canals, who succumbed to diseases that swept through the crowded, unsanitary conditions of medieval work camps, who were crushed by falling stones, or whose bodies simply wore out from decades of exhausting physical labor that left them broken by middle age. Their names are mostly forgotten and their graves are unmarked or lost, but their contribution persists in every building that still stands, in every canal that still flows, in every bridge that still crosses water that refused to become solid ground, but that Venetians convinced to support a city anyway. Venice survives tonight not through inevitability, but through continuous intervention that recognizes the city will sink without pumping to control groundwater, will flood without barriers to block storm surges, and will eventually succumb to rising seas unless climate change is addressed at scales far beyond what any single city can influence. The wooden pilings driven into lagoon mud more than 1,000 years ago remain mostly sound despite carrying loads their installers never imagined, testament to construction quality that exceeds most modern buildings' expected lifespans. The canals still flow with tides that bring fresh water in and carry waste out in cycles that have repeated billions of times since the first refugees arrived seeking safety in marshland that no one else wanted. The bridges still arch over water that separates and connects simultaneously, serving the same purposes they served when they were new centuries ago. And somewhere beneath it all, buried in mud and hidden by water, 10 million wooden stakes hold steady. Ancient forests converted into foundations, trees that died so buildings could rise, timber that became stone through centuries of pressure and mineralization. Proof that human determination can make the impossible permanent if the effort persists long enough, and if each generation maintains what previous generations built, rather than allowing neglect to undo what labor created. Venice rests tonight on its buried forests. 10 million wooden stakes driven into lagoon mud across 15 centuries. Oak and larch poles that have stood submerged for generations beyond counting. Foundations that no one will ever see again. but that continue supporting marble palaces and stone churches and brick houses that rise above water, reflecting moonlight in canals where boats moved silently through darkness, just as they have moved for more than 1,000 years. The city sleeps as cities do, lights dimming in windows, footsteps fading from narrow calle and bridges arching over water, the sounds of life quieting to whispers and then to silence broken only by water lapping against fondamenta walls and by distant bells marking hours that pass regardless of whether anyone remains awake to count them. The wooden pilings remember nothing. They possess no consciousness, no awareness that they support buildings where humans live and work and die, no knowledge of the centuries they have endured or the weight they have carried. They simply exist as wood exists, cellulose and lignin gradually transforming into something harder as minerals replace organic material molecule by molecule, a process so slow that even across centuries the change is incomplete, leaving them suspended between what they were as living trees and what they are becoming as fossils buried in clay that will eventually compress into stone if enough millions of years pass without disturbance. The pilings ask nothing and expect nothing. They hold their positions because physics and chemistry leave them no choice, because the forces pressing down from above are balanced by the resistance of dense clay below, because equilibrium was achieved when they were driven to proper depth and has been maintained through time that moves forward relentlessly, whether foundations hold or fail. The buildings that stand on those pilings carry histories written in stone and mortar. St. Mark's Basilica, with its Byzantine domes gleaming even in darkness, because gold never stops reflecting whatever light reaches it. The Doge's palace, with its pink and white facade that has watched empires rise and fall, while Venice itself transformed from republic to Austrian possession, to Italian city struggling to survive the twin threats of sinking and tourism that hollow out the population that might keep it alive as something more than a museum. The arsenal's fortified walls enclose basins where warships no longer are built, where the industrial efficiency that once made Venice feared throughout the Mediterranean has given way to cultural events and exhibitions that fill spaces originally designed for rope walks and ship timbers and the organized chaos of production systems that anticipated modern assembly lines by centuries. The canals flow with tides that care nothing for human construction. Twice daily, the Adriatic pushes water into the lagoon and pulls it back out again, rhythms that predate Venice by millions of years and that will continue long after the last building collapses and the last canal fills with sediment and the lagoon returns to being what it was before refugees arrived, fleeing barbarians who destroyed their mainland homes. The water is patient in ways humans cannot comprehend. It surrounds the wooden pilings and the stone foundations. It seeps into every crack and gap. It waits for mortar to fail and for wood finally to rot, and for the buildings to settle just slightly more, until the process that has taken centuries accelerates into decades or years, or one catastrophic moment when equilibrium that has held for so long finally breaks, and what was solid becomes liquid again. The bridges arch over darkness where moonlight doesn't penetrate. Stone spans that have carried millions of footsteps, that have felt the weight of handcarts and the passage of couples walking together, and the hurried crossing of residents who barely notice anymore that they are traversing water on structures that represent engineering solutions to problems most cities never face. The Rialto still stands where it has stood since 1591. The same stones, the same arch, the same foundations on the same pilings driven into the same mud. 4 centuries of continuous service without the catastrophic failure that skeptics predicted when Antonio da Ponte proposed his design, and that critics still mutter about while walking across the structure that has outlasted them all. Imagine Venice as it appeared to the first refugees who arrived in the 5th century. Mudflats and marsh grass, shallow water where the tide decided what was land and what was sea, islands barely rising above the lagoon surface. A place so marginal that no one had bothered claiming it before desperation made marginality look like opportunity. Imagine the decision to stay rather than to retreat once the immediate danger passed, to drive the first wooden stakes, to build the first permanent structures, to commit to making this impossible place into home rather than temporary shelter. What faith did that require? Or what stubbornness, or what recognition that sometimes the impossible is merely the difficult approached with enough determination. The workers who built Venice across 15 centuries are gone. The pile drivers who hammered wooden stakes, the masons who laid brick and stone, the bridge builders who calculated arches, the dredgers who shaped canals, the carpenters who framed roofs, the artists who decorated churches, and all the countless labourers whose names were never recorded and whose contributions went unacknowledged, except in the aggregate statistics that track how many tons of stone were moved or how many cubic meters of mud were excavated. They lived and worked and died building something larger than themselves, knowing or perhaps never knowing that their labour would create permanence that would outlast empires and ideologies and all the political systems that rose and fell while Venice endured. Rest now. Let the image of Venice carry you towards sleep, a city floating on wooden pilings, buildings rising from water that should prevent construction, bridges connecting islands that geography tried to keep separate, canals serving as streets where boats glide instead of carts rolling. The impossibility of Venice matters less than its existence. The fact that it stands tonight after more than 15 centuries proves that human determination can convince even lagoons to become foundations, can transform wooden stakes into platforms for marble palaces, can create beauty and permanence in places where nature intended only temporary occupation by simple communities content with fishing and salt production rather than maritime empires and artistic achievement. The Meuse barriers rest on the seabed tonight, hollow steel gates waiting for the next storm surge that will require their activation, modern engineering protecting what medieval construction created, technology that would seem like magic to the workers who drove the first pilings, but that serves the same purpose of keeping Venice dry enough for human habitation despite water that surrounds and threatens always. The barriers will rise when needed and fall when danger passes. They will function or they will fail. They will protect for decades or prove inadequate sooner, and their ultimate fate remains unknown, just as the original pile drivers couldn't know whether their wooden stakes would support buildings for years or centuries or millennia. Sleep well. Venice watches over its lagoon. The wooden pilings hold steady beneath, stone and marble. The canals flow with eternal tides. The bridges arch over water that connects and separates. And somewhere in the darkness a city rests that exists, because people refuse to accept that some places are too impossible for human ambition, that some ground is too soft for construction, that some dreams are too unrealistic to pursue. Venice stands as answer to all those who say something cannot be done, not through single dramatic achievement, but through accumulated labour of generations who built slowly, carefully, patiently, who drove one piling at a time, laid one brick at a time, carved one canal at a time, until impossibility became merely improbable, and improbability became historical fact that tourists photograph, and that historians study, and that tonight floats peacefully on buried forests that turned marshland into foundations strong enough to support a civilization. The lagoon holds Venice in its embrace, neither quite land nor completely water, but something between that humans shaped into home through determination that outlasted empires, and through engineering that turned wooden stakes into eternal foundations. Rest now. The city sleeps, the pilings hold, the water flows, and dreams built from mud and wood and stone endure through centuries that pass like tides. Inevitable, relentless, eternal. Good night.